Welcome to this lesson about fundamentals of energy and energy conservation. In this video, we deal with the concept of conservation law, principle of virtual work, and the Lambert principle. Let's begin with the conservation law, and in particular with the concept of energy. So, the conservation of mechanical energy. The mechanical energy is a scalar defined as E equal to K plus U, where K is the kinetic energy and U is the potential energy. The energy of an isolated system is constant. Isolated system means that it cannot exchange interaction with the environment, or the interaction does not produce any sort of work. Let's make an example. In this example, we have a roller coaster that can be seen as an isolated system, and if we neglect drag force and friction between rails, the only interaction are the rail constraints, which produce a force which is always orthogonal to the motion, so it does not produce any work. In this case, we have a conservation of energy, so the initial kinetic energy and the initial potential energy, and at the end of this slope, we have the final potential energy and the final kinetic energy. So, since the energy is constant, the energy at the initial time is equal to the energy at the final time, which is equal to the kinetic energy at the initial time plus the potential energy at the initial time equal to the kinetic energy at the final time plus the potential energy at the final time. Now let's define the linear momentum. The linear momentum of a body is defined as P equal m times v, where v is the velocity and m is the mass of the body. P is a vectorial quantity. The linear momentum is a vectorial quantity. So particles in general can exchange linear momentum with each other, but if no external forces are applied, the total quantity of linear momentum must be constant. Let's make an example. We have two rolleys with two different masses, and they are kept together with a rope, but they are pushed away with a spring. At the beginning, they are both at rest, but when the rope is cut, the spring pushes the trolleys in the opposite direction. At the beginning, we have that the linear momentum is equal to 0, because they are both at rest, and at the final time, we had the linear momentum is equal to m1 times v1 plus m2 times v2, which means that v1 is equal to minus m2 over m1 times v2. Since we give the masses 0.5 kilograms and 0.25 kilograms, the velocities at the end will be the double of the other. Now let's define also the angular momentum. The angular momentum of a particle is L equal R cross product P, where R is the distance between the particle and a pole, and P is the linear momentum. In an isolated system, the angular momentum is constant. Let's see another example. If we consider a disk of radius 2 meters, rotating with an angular velocity n of 1 over 5 revolutes per second, and a rotational inertia I of 500 kilograms square meter, and a children which mass is m equal 25 kilograms moves from the center and stop at the border of the disk. In this case, we have that the angular momentum is equal to the moment of inertia times the angular velocity at the beginning, which is equal to the moment of inertia times the angular velocity at the end plus the mass of the children times r squared and the rotational velocity at the end. Resolving this equation, since the angular momentum must be constant, we have that the velocity at the final moment will be equal to the velocity at the initial moment times the inertia over the inertia plus the mass of the children times the radius squared, which will be equal actually to 1 over 6 revolutes per second. Now let's state the principle of virtual works. Let's define a virtual displacement, delta S, which is an arbitrary infinitesimal change in the position, which is consistent with the constraint imposed on the motion. We can also define a virtual work, dl, which is done by a force, and it is defined as F times delta S. A virtual work, delta L, done by a momentum will be defined as m delta phi. So the principle of virtual work states that the necessary and sufficient condition for the equilibrium of a particle is zero virtual work done by all working forces acting on the body for any virtual displacement delta S consistent with the imposed constraint. The principle of virtual work, PVW, can be used in statics for the solution of equilibrium problems. It's important to note that no virtual work is done by internal forces, reaction is smooth constraint, or by forces normal to the direction of motion. The virtual work is done by reaction when friction is present. Let's see an example. In this example, we have a motorbike rear suspension. Q is the generalized coordinate which describes the angular motion. So Q is this angle here. K is the spring stiffness, which is opposed to the force F applied at the end of the swing arm. So if we apply the principle of virtual work, we have the total work must be zero. So delta L external forces will be equal to delta U spring, where U is the potential energy of the spring. There is only an external force applied to this system, so the virtual work of the external forces is equal to F times delta Y, and delta Y is equal to L delta Q. We can write down that the virtual work of the external forces is equal to the force times L times cosine of Q delta Q. For the spring, we can write down that spring length at rest is S0. S is equal to the square root of Sx squared plus Sy squared. And we can also define that Sx is equal to B cosine of Q and Sy is equal to H minus B sine of Q. So if we plug in those two definitions in the definition of S, we can write down that S is equal to the square root of B squared minus 2HB sine of Q plus H squared. We can also write down a kinematic relation for delta S and write down that delta S is equal to ds over dq times delta Q, which is equal to minus HB cosine of Q over the square root of B squared minus 2HB sine of Q plus H squared times delta Q. And therefore the work done by a spring is UP is equal 1/2 K times delta L squared, which is equal to 1/2 K S minus S0 squared, and the infinitesimal work is delta UP equal to K times S minus S0 times delta S. And delta S we have already defined above. Therefore, with the principle of virtual work, we can write down that FL cosine of Q delta Q is equal to minus KHB cosine of Q times 1 minus S0 over the square root of B squared minus 2HB sine of Q plus H squared times delta Q. Since this equation must be true for all delta Q, we can simplify then delta Q and write down that FL cosine of Q plus KHB cosine of Q times 1 minus S0 over the square root of B squared minus 2HB sine of Q plus H squared is equal to 0. Thanks to this formulation, we can now find out the value of Q, since we already know F, B, H, K, and S0. Now let's define the D'Alembert principle. We can extend the principle of virtual work to dynamics problem by introducing the concept of an inertial force. So from Newton's second law, we have that the force is equal to the mass times the acceleration. And now we can introduce an inertial force, which is F star, equal to minus the mass times the acceleration. The total force will be equal to the force plus the force star and must be equal to 0. Therefore, the virtual work done by all forces must be also equal to 0. And let's see an example. We have this Atwood machine. The state of this machine is determined by the position of the two masses along the U-shaped coordinate S, which is looping over a frictionless pulley with the string. So the work done by gravity is the work done by gravity on the left-hand side, which is minus mg delta S, and the work done by gravity on the right side, so delta WR is equal to plus the mass times g times delta S. So the work done by the inertial forces will be equal to minus the big mass plus the small mass times the second derivative of S over time times delta S. So we can write down that the total work is big M minus M times G minus big M plus M times the second derivative of S over time, all times delta S, which must be equal to 0. And this must be true for all delta S. Therefore, we have that the acceleration of S, so the second derivative of S over time, will be equal to G big M minus M big M over big M plus M. So we must also note that the force of constraint in the center of the pulley do not enter in this problem. The lesson is over. I will leave you some references of those topics.